Hello and welcome to the Dialectical. This is a channel where we will be discussing all your favorite dialect-related subjects and topics. The purpose of today's session is to go through the latest dialect release on what causes relativistic mass, in order to react, discuss, give commentary, and flesh out some of its ideas and topics in greater detail, as well as respond to some of the many viewer questions, critiques, and objections the video has received. Here to help with that today is James Ellias, the independent thinker and individual behind the Dialectical channel. Hello, Mr. Ellias. Is there anything you'd like to say before we get going?
Yeah, well, thank you very much for having me on. I've been watching Dialect's videos for years now, and they've influenced my thinking to some degree. And when I met some of your representatives at the PAMO conference, I was really glad that your organization agrees with my approach. And our common approach here is that we're not satisfied to just look at the mathematics. We're not satisfied to just say, oh well, the math gets correct predictions, so that's enough. No, we want to identify the actual hidden entities that are behind the phenomena we see, so we can identify new cause and effect relationships. And this video is one of those attempts, so I'm really excited to get into it.
All right, great. So basically, this is going to be a pretty informal and structured kind of thing. We're basically going to play the dialect video and just kind of watch it along with the viewers, and then whenever you want to stop to raise a point or elaborate or something or have a question, just start talking, and I'll pause the video here on this end and we'll discuss. All right.
One of the strangest consequences of relativistic physics is that the mass of a body should increase with its speed, a fact closely related to the impossibility of superluminal travel. While special relativity posits that this phenomenon must be true, the theory has never been able to offer any physical mechanism by which a body of mass should find its inertia increased in consequence of its motion.
All right, first remark, just wanted to make there real quick about special relativity and positing the phenomenon of relativistic mass. So strictly speaking, special relativity derives relativistic mass, but it does so by assuming the principle of relativity to be true, that the laws of physics take the same form in all inertial frames of reference. We felt, however, that it was fair to say that this phenomenon is posited because special relativity, it doesn't really offer any kind of causal explanation or any mechanistic way to uncover what's going on, and so it kind of just presents these phenomena like relativistic mass or time dilation or length contraction as being just brute, intrinsic facts about how a reality just really is, and that there's nothing deeper.
And further, what I would add is that I think people might say, well, that's not really a problem because every theory, proposes basically it explains some facts in terms of other facts, and those deeper facts are just sort of posited, right? And every theory is going to be that way. For example, like Newton's theory of gravitation was perfectly fine, and people asked him, well, why does mass produce an attractive force? And Newton just says, I don't know. I'm not going to speculate about that because we don't have evidence that tells us the answer, but we know that it does produce a force. So that's not the problem with special relativity, that it leaves some things unexplained, because every theory is going to do that. The problem is that the way it explains things closes the door to further explanation. It says, in effect, that's just the way space-time is. That's just the intrinsic nature of space-time, and then from that relativistic mass is derived, and many other things are derived. And so you get a framework where you can't identify the causal processes that give rise to these phenomena, because it's just, that's just the nature of space-time. The end. Well, why is space-time that way? Space and time are just like basic facts of existence, so you can't explain their nature. They just have that nature, and anything follows from it. But that's,
yes, you're absolutely right. It really shuts the door to further understanding, and because as soon as you try to ask for further understanding, it's read as objecting to the validity of the theory altogether. So
yeah, but I mean, I don't know about you, but that's exactly what I question. I think that these phenomena are the result of entities acting on one another, because that's the real nature of reality, is that it consists of entities that change in accordance with the way they act on one another. And space and time are just relationships between entities and their actions. And so if you start,
I could go on. I could go on that subject for hours.
It's because it does. Yeah, it's. We've only gotten 25 seconds in, but yeah. So
I know.
It's just.
We better keep
I'll
going.
just say that closes the way it does it. It closes the door on further explanation.
Right. And so so one of the purposes of making this video on our end was to try to show people that you can keep asking questions and you can keep getting answers. So
yeah,
hopefully we'll find some along the way here. All right, let's keep going.
Hence, there remains no satisfactory answer as to the question of why matter shouldn't be able to surpass the speed of light. Could such a physical mechanism behind relativistic mass really exist? And if so, how might we go about uncovering it? This is Dialect with the problem of relativistic mass.
We have a quote from Schrödinger here.
Yeah, I really like this.
He was the big wave guy.
Everyone is familiar with the famous equation E equals mc squared, but there's a secret behind its meaning that's almost entirely unknown. No, it's not just that this equation can be derived classically without any reference to the postulates of special relativity whatsoever, a topic we covered in a recent video, but it's that this famous expression is actually a wave equation. That is, given any classical mechanical wave system under certain ideal conditions, there's a special relationship between the energy of a wave traveling in that system, the speed of that wave, and the momentum the wave imparts in the direction of its travel. E equals P times C.
All right, so we're going to pause real quick here because this expression is probably the most important in the video as it informs everything that's to follow. The idea of of the energy of a wave being proportional to its momentum is what leads to essentially relativistic mass. But this is entirely a classical expression, and it's maybe not immediately obvious why this is so. To understand why a wave of any sort has an energy that's proportional to its momentum is actually a pretty kind of in-depth and complicated topic. Something we would like to go into, but it's outside the scope of this video. It is very empirical. Any classical wave system you observe will obey this relationship, and it's important to note that going forward.
Now, it's also, first of all, what I really want to add at this point is anyone who's confused, there might be people who are very legitimately confused, like, well, why are you talking about waves? Like, I thought we were talking about matter and how it has energy. Why are you bringing waves in? Well, the reason is because we both entertain the hypothesis that matter really is a wave. And I mean, this is directly observed from quantum phenomena, that matter, electrons, protons, neutrons, they act like waves, even though they have matter or they have mass, like they act like a wave. And so it's a very reasonable hypothesis that there's an ether or a plenum and that matter is just a wave in this plenum. And E equals MC.
Yeah, we'll touch on that.
We'll get to that
just
in a
1
moment.
minute here. Yeah.
But that's why we're thinking about this is energy as yeah.
Yes.
It's a relation found in all sorts of real-world systems, from sound waves in acoustical mediums, to waves on strings, and even water waves to some extent. Now, the fact that waves carry such momentum allows us to do something very interesting. In accordance with Newton's laws, we can divide a wave's momentum p by its speed c, and in doing so, assign that wave a mass m. This in turn yields a second expression for wave momentum, which, when plugged into the expression for wave energy, yields E equals mc squared. Thus, we see what this famous expression is actually telling us is that a wave traveling with energy E and speed c behaves exactly as though it were a body of mass m traveling with speed c, with m equaling E over c
All right, so
squared.
here's definitely a very important point to stop, and a place I could have used a little more explication if there had been more time. This is another very crucial aspect of the video, in which basically the idea of mass wave equivalence is put forth. So when we say m equals E over c squared, we're not saying that the literal mass of that wave, if you could draw like a box around where the wave is happening, in a classical system where you have something waving like here, like masses on a string, if you draw a box around that wave, the actual mass content in that box is not this m value here. Rather, when you have a wave and it transmits a lateral momentum, because of that momentum, because there's momentum and speed, you can treat it just as though it were like a regular kind of Newtonian-style billiard ball mass, which has a value of mass, but the value of mass it has is now going to be proportional to its energy. So it's a different thing. The mass isn't real; it's kind of equivalent mass, but it allows you to treat the wave as though it were a body of mass.
Well, it's very real. It's just not it's not quite as literal as you might think. Like the mindset I come at this from is that, again, there's an ether, and matter, mass are waves in this ether. And if you want to speed that wave up, and the wave acts as an entity. The wave is this whole unit that acts really as a whole. It's not just the movement of its parts. It acts as a whole structure. And if you want to accelerate that structure, there's an inertia. And when that movement structure moves along, it carries momentum. It carries the ability to make other such movement structures move. And that's its momentum. And here we see like the ratio of the momentum to the speed. That's what we're defining as mass. And so it's a subtle understanding of what mass is that goes along with this very reasonable hypothesis that masses are waves in the medium.
Right. So to our many of our viewers are still a little ether averse. So we should note that this still applies even if you don't like the ether and you just want to take the abstract field view. And there's lots of evidence that suggests that particles are kind of waves within these fields. And on the whole, this is sort of where where we're headed with this video. But I think something really fascinating that comes out of this idea is it kind of starts to help us understand why for so long that there's been this particle wave divide in our modern physics. Like how is it that sometimes things act like a particle and sometimes they act like a wave? Well, here's a very perfect example of something which is a wave that also has a way you can formulate it and frame it to make it behave like, in which it behaves like a particle.
Yeah.
So it's not actually a particle, but you can treat it like it in certain circumstances.
Because waves act like particles in this fashion, especially when you zoom out.
Right. So you can treat any wave as though it were a body, a particle with a certain mass. Now, it doesn't actually have that mass like you would think with a particle, but you can treat it that way, and it is, physically equivalent. And so as you say, the inertia is very real, and we're going to hear that in 1 second.
Or, in other words, waves carry a very real inertia proportional to their energy content. Note that none of this requires any sort of spooky space or time relativism. Rather, it all just follows from very basic, straightforward
So this
wave
is the
mechanics.
other very important point to stress, is that, we are sort of presenting a new way of looking at things, but it doesn't require any sort of new ad hoc postulates about the nature of reality or, crazy out there ideas. We are kind of like trying to go from this billiard ball style Newtonian way of thinking to that classical mechanics to now a kind of fluid wave mechanics. And they're different, but they both conceptually fall under the same framework, and you don't need any new craziness to throw in there to make it work.
Yeah. People have often, everyone in physics talks about the classical quantum divide, and they talk about the classical / relativistic divide. And that divide is fundamentally, that divide is marked by a change in mindset about the metaphysics, about like, well, what's the basic nature of reality? Is reality quantum? Is reality this non-absolute flux, or they'll say, at first we thought reality was just a bunch of entities acting on one another, but then we realized like, oh, well, it's actually just space-time. It's actually just this space-time geometry structure. So what we're realizing is that we don't need to fundamentally alter like the basic foundations of metaphysics with no evidence, by the way. I think all of that is just wrong metaphysically, but we don't have to. But what we're here to say today is we can account for all of these phenomena without a change in metaphysics. We can still just talk about entities acting on one another. It's just that the entities are now parts of an ether, where each part of the ether acts on each other part of the ether in this wave manner. And really the classical quantum divide, or the classical relativistic divide, is really just a particle wave divide, realizing that these things that acted like particles, when you zoom in close enough, that particle nature is an emergent property of the underlying wave nature. Maybe that's the right divide, not a metaphysical, these radical new metaphysical postulations that are just wrong anyway. But just, hey, it's a new mechanics. It's just a wave mechanics instead of a particle mechanics.
Yep, I think that's precisely apt and perspicacious thing to say, because it's, again, if you have just like a simple wave on a string, you can reflect that wave. You can just treat it in certain circumstances. You can just treat it as a particle that moves back and forth, in the way that with regards to how it interacts with other waves or other particles. So in many contexts, you can just treat a wave as a particle, and that's fine for what you need to do. But then there will be contexts in which that no longer holds, and I think that's where you get into the kind of all the fuzziness of quantum mechanics and everything like that.
And that's the real divide, not a metaphysical divide. Yeah.
Yep, 100%. All right.
And such mechanics were in fact the lens through which mass-energy equivalence was first discovered in the year 1900. This was when the French mathematician Henri Poincaré realized that in order for Newton's third law to be reconciled with electromagnetism, electromagnetic waves had to carry both momentum and mass. Subsequently, he was able to show that electromagnetic fields have an inertial density proportional to their energy density.
Something really interesting about Poincaré's proof. So he proved E equals mc squared in 1900, and he did it by treating the electromagnetic field as a fluid. So he was inadvertently using wave mechanics without explicitly acknowledging wave mechanics. So when he did his proof of E equals mc squared, he didn't, it seemed very specific to electromagnetism. He didn't understand exactly that, E equals mc squared can apply to any classical fluid or wave mechanical system. Yet he was kind of making that connection. So he referred to the electromagnetic field as a sort of fluid whose inertial density was given by E equals E over c squared. And so what this really showed was basically that light is a classical wave system, just like every other classical wave system. He just wasn't up enough in classical wave mechanics to be able to draw that connection.
With the constant of proportionality being 1 over the speed of light squared. The implication was that light itself both carried and transmitted mass, a fact next grasped at, but not truly comprehended, by the individual whose name would soon become synonymous with E equals mc squared.
All right, so you have to give us your opinion on the AI, the use of AI in the video.
I really liked this. I really liked this stuff.
Viewers were a little divided on it. Yeah,
the only hazard I see here is that you're bringing them to life, which I think is just marvelous, because we read these people and they're all characters in a drama that has affected our lives. And so like bringing them to life is so vivid. There is a little bit of a hazard, which is you might be ascribing sort of physical mannerisms to them that they didn't have. So you might not be like,
that's a great point to bring up
there, but like it's worth it. It's so cool. So
yeah, like in the production phase, like you'd put in, prompts to the AI and it would come back with several different options. And some of the times the way they moved was like so modern. You're like, no, there's no way they would have moved like that.
Mm-hmm.
It was, yeah. So you do kind of feel like a little guilty, like I'm kind of telling something of a lie, but at the same time, it's we thought it was a nice, fun touch and adds a little bit of relief to the otherwise serious nature of the video.
Mm-hmm.
Indeed, in 1906, fixated on the idea of mass-energy equivalence, Albert Einstein set out to rederive Poincaré's 1900 E equals mc squared result, though he adopted a much simpler approach. Expanding upon a scenario considered by Poincaré, wherein a body of mass emits a burst of radiation and recoils, Einstein recognized that if the radiation emitted by the body was assumed to carry away only energy and not also mass, then this would lead to the possibility of perpetual motion.
Can you explain that a little more? I in my first watching, I didn't have time to fully work that out in my mind.
So Einstein made this argument, right? Basically, you've got a box and you shoot a radiation from one end block to the other. Mm-hmm. Because the radiation carries momentum, the box moves to the left. Then that radiation gets absorbed on the right side of the box stops moving. So basically, energy went from the left side of the box to the right side of the box. So Einstein was like, well, if energy can, be transported without also mass, then there should be basically a massless way of transporting energy that we could then use to take the energy.
But when you sent it back, when you returned it back to the left, wouldn't that bump the box to the right again, and then you'd never actually change the center of mass of the. So, yeah.
Einstein said it was a little more complicated. He had like some massless transport system that he described in his paper. And yeah, to be fair, it is a little confusing.
Yeah, I mean, he'd have to prove that massless transport of energy would even be possible going the other way. Or not massless transport, but like impulseless transport. See, when we transported energy, if we proposed that we transported energy from the left to the right without transporting mass, like, okay, fine, maybe. In fact, that's how most people think of it. But you put impulse to the right. Now, if you transported the energy back to the left, then you'd have to then put impulse to the right, unless you came up with some new way of transporting the energy. And if impulse went to the right, then you'd never be able to do this perpetual infinite acceleration business.
Yeah, so I think that's a fair objection, and it confused us as well, definitely on our end. I think, but the idea was that if there would be a way to, if things could have energy, not mass. And so this is an important point. Like he was basically arguing if things could have energy, not also mass, then there ought to be a way to transport energy without using mass. I think that was the primary point of his argument. And so that's what when he says, it is very important to understand here, like mass energy equivalence is also, on a personal level here, I think it's a poor terminology, because people think, oh, mass and energy are now the same thing. No, they're proportional. And what Einstein shows here is that where you have energy, you also have to have mass. Like the two go together. They're not the same thing. They're definitely, they have very strict definitions. They're obviously not the same thing by definition. But where you see one, you must see the other. And you see them in this specific proportional relationship. And so I think Einstein's argument was, if you could just see energy without seeing mass, then there would be a way to transport energy without having to involve mass. And that way could be exploited to take the energy that was moved from one location and went back to an original location, in which case you could use that to indefinitely change indefinitely translate a body of substance.
Yeah, I see the argument, but I think there's like to me, it seems like there's a hole, which is that maybe you could transport the energy back to the left without transporting mass. But how do you know you can do that without producing an impulse to the right? Because when the light beam shot from left to right, there was an impulse to the left. When the energy returns from right to left, how do you know you can do that without producing an impulse to the right? And if that happens, then you'd never have perpetual motion. But I mean, I have a completely different reason for buying this argument, or I don't know if I buy Einstein's, but I buy your reason for taking this seriously. So like I asked you at PAMO, I asked, well, why the hell would you, it seems like you're redefining mass is basically what I said. See, to me, mass is like, it's a characteristic of these particular kinds of entities, but now you're ascribing mass to light waves, basically. So why would you do that? And you basically,
I think we can return to that question.
And we're going to see that in just a moment.
Yeah.
So why would you do that? I'll leave that open for the audience.
Just specifically regarding, is Einstein's proof have a hole or is it flawed? It has been discussed by scholars, and one of the papers linked, the first paper linked in the video description
talks
about it, and he actually offers an alternative way involving a gyroscope or something.
Oh.
We didn't quite understand it, but I mean, it's also similar to, if you think about it, similar to Poincaré's derivation, because Poincaré derived it assuming that, he only assumed that electromagnetic waves had to carry momentum, and then basically by knowing the speed of that wave and assigning, knowing the momentum, you could assign it a mass. So I mean, there's some question to it. Yeah, for sure. I think that's a fair point to bring up, and we'll get to it.
To avoid such an outcome, Einstein imposed a stationary center of mass condition upon the system, and subsequently calculated the amount of mass required to be carried away by the radiation to be equal to that radiation's energy content divided by c squared. Now, like Poincaré's proof before it, Einstein's derivation here was entirely classical, and therein lay its true value. But Einstein never understood the full implications of his work. That is, he recognized the first half of the picture, that because bodies exchange, emit, and absorb radiation, their inertia is dependent upon their energy content. However, in his desire to abandon classical thinking, he missed the second half, that this energy content relates to inertia in precisely the quantity that it does because of wave physicality. That is, because light is physically a wave and waves physically carry inertia. This in turn
again, the
meant
point
Einstein
there was to emphasize, E equals mc squared is not some arbitrary expression. It's not E equals 3/4 mc to the third or something. It has this very specific relation because it is a relation that comes from wave mechanics. Literally everything about the math tells us, that light acts just like a classical wave system. And I've paused it here on a really freaky AI.
That doesn't look freaky to me.
Can you see his eyeballs?
It doesn't look that weird.
Yeah, you can tell the AI is still struggling a little.
Maybe I don't have a very clear image on my side. So I want to say you just the video just mentioned what my reason is for buying this, which is imposing a stationary center of mass condition. So
yes,
if you want to if you want to redefine mass, to do this, I think you have to redefine what mass is. And as far as I know, you have to redefine mass based on an imposition of a unchanging center of mass. You have to say it's important that we think of a set of interacting entities as maintaining their center of mass over the course of an interaction. And if you do that, you have to ascribe mass to light. Now, I entertain that.
But are you saying that's empirical, or is that a framework you're adopting?
That's a framework I'm adopting, but more importantly, it's not an arbitrary framework. It's not just like, oh, well, I felt like doing that. It's that, well, if we redefine mass to represent this, then I haven't thought too much about this, but if you redefine mass as having this property that the center of mass of a set of objects will always stay the same, you've now reframed your concept in such a way that it is able to capture a very real fact that once again, like these entities interacting with one another, not just masses, but also light, these entities interacting obey a certain rule, obey a certain nature. And the only way to capture that nature conceptually is to reconceptualize mass and then impose this stationary center of mass condition. That seems like a solid argument for redefining mass, but I think it's important to note, like, that's the justification, and you are redefining mass when you do this. So it's not obvious. Okay, what do you think of that? Do you think that you guys have actually redefined mass here?
I'm not sure I would agree with that entirely. I mean, it's still the same definition of mass, P over V, that Newton uses. But I mean, you do bring up some deep philosophical issues, like how much of the conservation momentum is empirical, and what part of it maybe is conceptual framework. And that's a harder thing, for me to sit here and kind of sort through at the top of my head.
Yeah, in my theory of induction, the way I see it is that concepts are man-made. You get to when you say a word, you get to mean whatever you want, but you don't get to. But some ways of conceptualizing the world are better than others. And so for me, the argument I can see for what you guys have done here is that if you reconceptualize mass, then you capture this fact about interacting entities, that if there's an interaction of light beams and masses, they will maintain their center. Center of what? Mass. Well, but to capture that fact, you have to reconceptualize what mass means. And that's perfectly fine, because mass meant something, because mass had its original definition because of certain facts observed in the world. Now we're observing new facts, and to capture them, we simply have to reconceptualize. And that's fine. We do that all the time. Yeah, that's how I see it. I'd be interested to know what, but yeah, to me, I resisted this in your equals MC squared video. So anyway.
No, it's fine. You should keep offering, resistance is important.
But then I ended up not resisting it when you said, like, well, we can redefine mass to maintain center, to maintain this rule of center of mass. And I bought that for the reason I just gave. That sounded right to me.
Okay. Interesting. All right, I'm getting scared of Einstein's demon eyes over here looking at me. He's chasing me from the afterlife here, so let's keep going.
Something remarkable that lay still further in his proof. Something which would have yielded all the content of special relativity without requiring any of its postulates. A completely classical derivation of relativistic mass. Now, to be fair, relativistic mass was never truly relativistic to begin with. The idea had begun being thrown around in the 1880s in the context of electromagnetic theory. And by 1904, the correct equations
I hope
had
you
already
paused and
been
read every one of
formulated
those.
Yeah, I mean, at some point I should. You mean in this timeline?
Yeah, it flies by, but there was a lot of research involved in digging up all their works too, especially. But it was interesting to see how each of them kind of built on the ideas.
Yeah, one of these days we have to have a discussion about your research on all of that, because I'd gain a lot from it. The history, I mean, that's the whole idea of the inductive method, is you dig up the history to find the original observations and reasoning steps that prove this stuff. So
Yeah, it definitely enlightens your perspective, and when you learn only the end result, you lose so much context and so much valuable insight, which is really unfortunate. But fortunately, physicists are not also historians.
Hendrik Lorentz, in his paper entitled Electromagnetic Phenomena in a System Moving with Any Velocity Smaller Than That of Light. The same paper where he published the famous coordinate transformations, which today bear his name.
Behind the scenes stuff here. Originally, we included all that stuff because we were planning on doing a little more Einstein bashing. Because Einstein's paper was also titled almost the exact same thing as this, and it came out a year later, which at the time, struck us as very, very suspicious given all the other terminology and stuff he appropriated without exactly crediting others. But it turns out that literally Einstein gets off the hook here because literally almost every paper had that title on this subject, like J.J. Thomson's and T.V. Side, Lorentz, Einstein, and then Planck. It's literally all the same title. So they all named it the same thing, I think, probably to signal to one another that it was content that they were all working together with. But yeah, there you can see the original Lorentz transformations. They're not quite in the form you're used to seeing them because he also performed a Galilean transformation before this, and that ends up winding up going in the X there.
Oh.
And then he threw in an L here that he later got rid of. He showed that was equal to 1. But yeah, to get from these transformations to Einstein's transformations, all you have to do is very simple algebraic manipulation. All right, a little history there.
Now, while in Lorentz's work, relativistic mass could be classically attributed to the additional energy and momentum carried by electrons in their fields, his derivation relied on the idea that electrons were malleable spheres of charge. Thus, its potential scope and veracity were limited.
So, Martin Mayer from the conference, he was big on asserting that electrons are kind of malleable, and he approached us a while ago and was trying to and claimed that the electron must undergo contraction when it's in motion. I think there's some evidence for that because Lorentz assumed it and it got the right answer, so there must be something truthful to that. Maybe the electron isn't just obviously if we're moving to a wave kind of model of things, the electron's not going to be a solid sphere anyway. But the idea that it contracts, I don't think is so unreasonable. Just a little note there.
Now, early derivations like Lorentz's were also not technically derivations of relativistic mass, but rather derivations of closely related concepts known as longitudinal and transverse mass. Now, in Newtonian physics, mass has one and only one definition: the ratio of a body's momentum to its velocity. But when deriving longitudinal and transverse mass, Lorentz and others were actually calculating the ratio of applied force to a body's acceleration, and designating this quantity as mass. But such a quantity is not mass. Rather, it should be more accurately termed effective inertia. Because force, as defined by Newton's laws, is not ma, but rather dp dt.
Okay,
or the
pause
rate
it
of
here.
change of a system's
I
momentum.
really
Yes.
didn't understand what
This
the
means-
distinction is because momentum, like a change in momentum, just is, a change in mass times the velocity. Or I'm sorry, a mass times. Oh, I think well, you're about to address this actually. Now that I'm thinking about it, because it's like because if the presumption that these two things are the same, it seems very reasonable, but that presumption presumes that the mass of the object doesn't change. That's the key, right?
Yeah, so you'll have to we'll pause in a little
And
bit.
we're about to
if
see
your
that, so let's just keep going.
confusion
Yeah,
is
okay. I'm
elucidated or
starting to
not.
put the pieces together.
Means the ratio of an applied force to a body's acceleration is in truth given by the expression dp dv, which reduces to m only in the instance in which the mass of a body or system can be said to not vary with speed. This overlooked distinction between effective inertia and inertial mass had very unfortunate historical consequences. when, in 1906, Einstein's mentor and publisher, Max Planck, became ardently confused about it in the course of giving the first general derivation of relativistic mass.
So Planck had the same confusion as
Yeah.
you, as we'll see here.
Is unable to grasp why momentum divided by velocity should give a different expression than force divided by acceleration, Planck wound up haranguing the idea of inertial mass altogether, declaring it to be a degraded concept that hinged on an arbitrary definition choice. This attitude was passed on to Einstein, who later famously declared relativistic mass to be ill-defined. Consequently, today relativistic mass has become something of a dead subject, with physicists often dismissing the idea as outdated, useless, or even misleading. But such an attitude is gravely mistaken, because as Planck and Einstein completely failed to recognize, these different types of inertia already exist in the context of Newtonian physics.
All right, before we get into the explanation of what, all this, why PORV is different than DPDV, I wanted to stop and address the, one of the primary objections the video got, which was, what about invariance mass, and what is invariance mass? So, when we were sitting down and writing all this, it was like, do we address the issue of invariant mass or not? And it was a big struggle. And in the earlier drafts, we tried to. The problem is that most viewers don't even understand what invariant mass even means to begin with. And so you have to go through the extra work of actually explaining it and then debunking why it doesn't actually represent anything physical. So what is your understanding of invariant mass? I'll ask you.
I could get into details, but I could say it quickly. I could say
yes,
invariant mass is a concept that it's the mass of an object for observers that are in the same inertial frame as that object. And
yes,
I would add that this concept is entirely framed within the context of special relativity, which is a theory I reject, number one. And then number two, this whole discussion we're seeing in this video takes place in a context of knowledge that predates special relativity.
That's a very good point.
You don't get to bring up invariant mass until after. If you're going to bring it up at all,
postulates of relativity.
Yeah, if you're going to bring it up at all, which I don't think you should, because I reject the special theory of relativity. But let's just say we haven't even gotten there yet. We're thinking of a historical inductive context in which people are building special relativity, and we have to be able to reevaluate the evidence that led to special relativity. We need to be able to think.
But you've dealt with this before, and you know what people do is they start out by assuming special relativity is already true, and then use that to argue why you need something like invariant mass.
Yes, exactly.
It's completely circular.
Yeah, and it's not scientific. It's taking a theory on faith.
Absolutely.
And what we're doing, even if now, we oppose special relativity, but even if we didn't, we'd still say, no, you don't get to use the concepts of special relativity while we're engaging in the thought process that allowed us to validate special relativity to begin with. You don't get to skip to the end and use the results of your proof in order to produce your proof.
Exactly.
Yeah.
It's like taking the results of the proof and using it as the premise. Yeah. And it is so frustrating.
Yeah. And now it turns out when you try to prove it from the beginning, you find that you can't. And that's why we reject the theory. And we find that there's a bunch of, there's all kinds of reasons I reject it. And I know the reason you guys reject it is because it basically comes from accepting a convention as though it's, the law of the universe, which is one of the flaws I agree with. There's other flaws in my view, though.
So there are many, yes.
Yeah.
So the invariant mass, briefly for the audience here, invariant mass is the rest mass of the body, but it has to be measured by an observer co-moving with the body of mass. So if you have an inertial observer and they're co-moving with the body of mass, they first have to adopt the Einstein synchronization convention. If they do that and they are co-moving with the body of mass, then they will measure the rest or invariant mass. But nothing requires that an observer adopt the Einstein synchronization convention. They can adopt a different convention and they will measure a different value for mass. So the whole idea that invariant mass is the only physically meaningful formulation of mass, which is an objection, the video got in his comments multiple times over. People said, so that's the only physical meaningful, way to define mass. It's not true. It's not physically meaningful. It's, it has a physical meaning, but it is a result of a measurement convention choice. So therefore, to say that it's the only thing that's real is to say, well, what you chose is the only thing that's real. it's that reality follows from convention, which is the biggest argument that we take against relativity. So we just wanted to address invariant mass, and it's really invariant mass is not relevant to this video at all. But because people start out by assuming special relativity is already true, they try to attack you and get you that way, which is unfortunate. All right.
For instance, consider the basic example of a rocket ship, which has to eject part of its own mass in order to accelerate. At any one instant, the rocket has a very real inertial mass, P over V, equal to whatever mass is currently in the system. And if the rocket were to shut off its engines and stop accelerating, it would be this value of inertia that would determine its resistance to any further force. However, when undergoing motion, the force required to accelerate the rocket, dp dt, picks up an extra term to account for the momentum of the departing mass. The effective inertia of the system is thus smaller than its inertial mass, because some of that mass departs the system during acceleration.
Let's pause and really.
Indeed, like relative.
And so we have two.
Yeah. So how's your understanding?
My understanding is slipping here because a lot goes by fast here. So let me get clear on the difference between inertial mass and effective inertia. So inertial mass is momentum divided by velocity. And then effective inertia is dp dv. So effective inertia is the mass that shows up in F equals ma, right?
Effective inertia is the ratio of F to A.
Yeah. So it's
wrong. It's wrong to write F equals ma to begin with, because that only applies to a specific subset of systems.
It doesn't apply to a case where the ship is ejecting mass.
Right.
Because you need...
So,
now, let's go back to that equation, actually, because I think part of what I need to understand that is this equation right here at the top. Yeah. So, or now it's at the bottom. So... yeah, this one. So
this one,
the total force is dp dt. Okay.
Yeah, you don't have to think about it in a calculus way, because calculus often gets in the way of understanding. Just think about it.
Well, no, I think I got it. So it's like it's the ma, but then
so the,
what's really going on here? I'm a little confused by this, actually.
So the momentum of the rocket, right? You've got momentum of the rocket. But then you've got the momentum of the ejected mass going the other way. Mm-hmm. And so you've got a momentum of a system, and force is you're calculating the change of momentum of the entire system, not just, what's still in the rocket, right? So if you want to apply a force to the rocket here, what you have to apply is less than what you would have to apply if its engines were shut off. If its engines were shut off, you'd have to apply force to move all of the mass inside of it too. All that mass inside would be resisting you. Mm-hmm. But here, when you apply that force, some of the mass is no longer resisting you because some of the mass is going bye-bye.
Right.
Some of the mass is helping you out.
Yeah.
It's helping you push. So the outside push that you have to give is less if it's already pushing itself. That's basically it. Does that help your understanding at all?
It only a little. So P in this equation, the green P, that's the momentum of the rocket.
In dp dt?
Yeah.
No, that would be the sum of the momentum. That would be the momentum of the entire system. So rocket and mass, ejected mass.
Okay, so the change in the total momentum over time is, of course, like, the acceleration of the rocket, the mass times acceleration of the rocket, minus the acceleration of the bits of exhaust that flowed out over the course of that small amount of time.
So the momentum, right, of the ejected mass is just the velocity of the ejected mass times the change in mass. So how much mass is getting ejected, right? dm represents the amount of mass that's leaving the system, and it's leaving the system at a velocity of the eject velocity. Mm-hmm. So it has its own momentum, whereas the rocket has the mass m and it has its velocity v. So you have to write the total momentum. The total momentum, if you wanted to write that as an equation, would be P equals P rocket plus PE. And then PE is negative here because it goes the other way. So then once you differentiate that with respect to T, you've got to account for the extra term that the momentum here that's leaving the system.
Okay, that makes perfect sense. How does this lead to two separate definitions of inertia?
All right, so it depends on whether the rocket is accelerating or not. So let's go back real quick. All right. So if you try to think about it in an instantaneous view, right? Mm-hmm. And think about mass here as a substance, because that's the easiest way to conceptually grasp it, right? There's literally a specific quantity of substance in the rocket, mm-hmm. right? And if the rocket's not accelerating, mm-hmm. So if the rocket isn't using its engines, then the inertial mass is just how much it would resist being pushed by an outside force. Mm-hmm. Okay, but now if that hand comes along and tries to push it while the rockets are already firing, it doesn't have to push as hard because some of the mass isn't going to be there when it's pushing. Mm-hmm.
However, when undergoing motion, the force required to accelerate the rocket, dp dt, picks up an extra term to account for the momentum of the departing mass. The effective inertia of the system is thus smaller than its inertial mass, because some of that mass departs the system during acceleration.
Okay.
Indeed, like relativistic mass, the mass of a rocket
while
is
undergoing the burn, its effective inertia, that is like the inertia, I mean, it's truly the effective inertia. It's like how much inertia does it have if a force acts on it? It's affected by the fact that it's constantly throwing out mass out the back over the course of that push. And
that's how I see it, at least.
The inertia is less. Yeah, I mean, that makes sense.
So hold on, I'll pause it in one second again here.
Velocity dependent. And also like relativistic mass, a rocket exhibits a divergent longitudinal mass, aka effective inertia.
So you can see from the graph, the effective inertia is less than the actual inertia, because if you try to push the rocket while the rocket's firing its engines, it's helping you do some of that pushing by ejecting its mass. So as you see, inertial mass here is dependent on how much velocity the rocket has achieved, because that's going to determine how much mass it is ejected. And then the effective inertia basically is the inertial mass, but it picks up a attenuating factor here. A very important thing to address here, which we would have liked to address in the video, but just cut it for time's sake. As you heard, so the longitudinal mass is the effective inertia. Yeah. The transverse mass is not. The transverse mass is the inertial mass.
Yeah, because it's not burning
Right.
in the transverse
So
direction.
to push it in the transverse direction, it's not going to help
yeah.
you do any of that pushing in this case, right? So that's why transverse mass is the exact same thing as inertial mass, which is a question that relativity has never answered really. So I kind of thought that was cool that it popped out of the classical formalism. But yeah, effective inertia only occurs in the direction of the system's acceleration, because that's how the system is already internally accelerating itself.
Yeah, I have a quick question here. So right now we're using the word mass, but it seems like it in the discussion so far, just with the rocket, we can and should only use the word inertia, it seems, because we're really talking about different ways of thinking about how the body resists acceleration.
Great
we're
question.
Not
so
primarily thinking about the quantity of substance in the body.
what do you believe to be the difference between mass and inertia, if you believe there to be one?
So I mean, mass is the quantity of substance in the body, and then inertia is this closely related resistance to acceleration.
I think that's the typical view. However, I don't think that's how Newton actually defined it.
Oh.
So I think that's sort of the common popular view of mass, and it accords with our everyday experience, is that mass is this quantity of substance of something that exists there, the material basis that exists in our reality, and that mass is a measure of that. But that doesn't actually follow from anything I think Newton actually ever wrote. And I mean, getting not 100% on this, but Newton basically, asserted that inertia and mass were kind of the same thing. A body's resistance to acceleration is its inertia, is its mass. It doesn't necessarily, never necessarily ever meant that there's a specific quantity of something there, only that what is there doesn't want to accelerate in a certain degree that you can put in proportion to other entities that don't want to accelerate to a certain degree. And I think we're kind of pushing up against that now with wave mechanics. We're taking the wave and treating it as a body of mass, because the measure of mass in a wave isn't the measure of quantity of substance that's there. It's a measure of how much motion is occurring and how much the medium doesn't want to, or how much the medium resists that motion.
Here's the way I'll tell you the way I've thought of it in the past, and then and I'll tell you how I'm modifying it in my mind right now, and I think it ends up agreeing with you. The evidence that I've given for myself for why we should treat mass as the quantity of substance is because when you take a given sample of material, let's say like a certain amount of iron or a certain amount of aluminum, you have no reason to presume that these, let's say you're in a context where there's no reason to think there's anything different between these samples. And if you simply double the volume of such samples, then you double the amount of material. You say, like, on the presumption that this stuff is uniform, and all the evidence points to it being uniform. There's no evidence that some part of it is different than the other parts. And if I double the amount and I double the volume of the substance, then I presume that I've doubled the quantity of stuff. Now, however, what you've given in this video is, in my opinion, so far, real evidence to redefine mass. Once again, to redefine it so as to preserve the center of mass of a set of interacting waves, that is, like matter and light waves. And if we redefine it that way, then we're forced to not think of mass as just the quantity of material. Why? Well, because there is evidence that when an object is accelerated, it gains this stuff. So we don't want to think of it as just the quantity of material anymore, because when it is pushed, like in Poincaré's box, when it gets pushed, it's ejecting something that allowed it to move. and that something should be thought of as it's light, and that light should be thought of as having mass so as to maintain the center of mass of the system as a whole.
I think this is probably the most deep and fundamental question of the video. It's like, what is mass? And I think let's shelve that conversation to the end, just because there is a lot of places you can go with it. It's a great question to ask, obviously. But yeah, we're dancing around like the idea of how correct are our conceptualizations, and do we need to reconceptualize them, or were they already this way and we didn't realize them beforehand, kind of thing. So yeah, I think we'll come back to that topic for sure. Well, let's keep moving for the moment.
The perspective we need then to understand relativistic mass is not that a body's inertia magically changes with its speed, but rather that, like an accelerating rocket, in order to change a body's speed, we first have to change its mass. And this is precisely what Einstein's 1906 paper proved. For in demonstrating mass-energy equivalence, Einstein also implicitly demonstrated that a body's change in motion requires a change in its mass, revealing at once the physical mechanism responsible for relativistic mass, a mechanism that will grant us more complete insight into the reason why matter cannot travel faster than light.
So at this point, do you feel like you have an understanding of what causes relativistic mass from the video so far?
Yeah, but it's rooted in my own way of thinking about this, which isn't the same as yours. The only way I can really get this to make sense is, once again, like, you got to redefine mass. And why did you do it? It's so that you could capture this fact about the center of something being maintained over the course of interaction. But the thing is that center of something, it's a real fact. But the only way to capture it is there might be other ways, but one seemingly legitimate way to do that is to redefine mass. That's why I'm
okay, two quick notes. Yeah, the center of mass thing, I think that's really about action-reaction. That's about Newton's third law, right? So we talked about this.
Yeah, but it's an extended sense of that, because you have to attribute mass to light in order to maintain the broader sense of the generalization.
So there is a big caveat to this video, which we didn't address. I want to go back real quick. Okay. So this scene real quick. So one of the earlier drafts of the video, we were tossing around the idea of not referring to wave mechanics at all, because you can, in fact, derive relativistic mass with zero assumptions of wave mechanics. However, we didn't go that route because we felt it'd be, obviously, wave mechanics is very central to physics, and we're headed down that route. But you don't actually need it. Now, I think this is important, and it will kind of help maybe your understanding. So this model here, right? This is a model where you have a body of mass and you have another body mass, and you shoot the first body mass the second, and then you assume an inelastic collision, right? They stick together and they keep moving. When you do that, then the mass of the system becomes, the mass of the original body plus dm, the mass of the small body. So you can derive relativistic mass by assuming just a complete billiard ball universe with no waves, just small masses that only travel at speed c. So I'll touch on this again later, but it is not necessary to assume wave mechanics to actually derive relativistic mass.
Wait, that all the masses
you can do
travel
it. There's
at
a term
C?
for this, for the theory where I forget it, but basically,
why would you presume they're all going C? Not.
I'll come back to this point. I think it may be a little clearer after the third act of the video.
And this is precisely what Einstein's 1906 paper proved. For in demonstrating mass-energy equivalence, Einstein also implicitly demonstrated that a body's change in motion requires a change in its mass, revealing at once the physical mechanism responsible for relativistic mass, a mechanism that will grant us more complete insight into the reason why matter cannot travel faster than light. Three crucial insights are thus needed to explicate the concept of relativistic mass. First, we must recognize that the expression E equals mc squared follows purely as a consequence of wave mechanics, rather than stemming from the postulates of relativity. Secondly, we need to recognize that a body undergoing motion is not a closed mass system, but, like an accelerating rocket, exhibits a continual flux of ingoing and outgoing mass. The last piece of the relativistic mass puzzle falls into place then, once we acknowledge that it is a body's kinetic energy which dictates this precise mass flux. For indeed, if radiation carries mass, then relativistic mass can be explained classically by simply observing the fact that the kinetic energy lost or gained by a body is physically indistinguishable from that body emitting and or absorbing radiation. That is, imagine a body of mass m traveling at some velocity v that is abruptly brought to a complete halt. Whatever kinetic energy it had due to its motion must now be entirely dissipated into the environment. Well, the theory of electromagnetism tells us that this energy is precisely carried away in the form of radiation, of light. But since that radiation also carries away mass, this means that by losing its motion, the body must also have lost mass.
Pause it real quick.
Meaning it's...
Yes.
What about uncharged bodies such as neutrons? I mean, if you bring those to a stop, they're not going to emit light. So wouldn't they not shed their mass in accordance with your new conception of mass?
So, important caveat to this video to address a number of objections that this model really only applies to, kind of basic mechanical accelerations. So if you want to start diving into the world of particle physics and stuff like that, does this model hold? We would say to some extent, yeah, but probably not fully, because you kind of losing the context.
Well, yeah, there's forces other than I guess the biggest, the most general way to show this whole or the most general way to identify what this theory isn't identifying is to just say, well, not all forces are electromagnetic.
That's one thing.
This reasoning does seem to apply to all electromagnetic interactions.
We just advised, this is a model for basic mechanical accelerations and bodies and their interactions. So a number of viewers brought up, well, how does in charge-to-charge attraction occur in such a model and stuff like that? And you really do have to dive into quantum field theory for those kind of answers. And, quantum field theory says that all that kind of stuff happens through virtual photons, whatever is meant by that. And so there's definitely a number of objections to the extent to which this model can be, truthfully applied, and we wouldn't advise anyone to apply it outside the context presented in the video itself.
So so it only applies to basically macroscopic bodies in mechanical.
To be safe, but we only advise applying to that
such
context.
Bodies aren't necessarily charged, so how would they shed when they're decelerated? Why would they shed light? Any rock is going to be uncharged, and if you decelerate it, no light is going to be emitted from that process.
So no, I don't think that. I'm not sure that's correct. I think uncharged bodies will still.
Maybe it would. Okay, I'm thinking. Okay, think of the following example, which would be imagine you. Imagine if. So
in most macroscopic collisions, kinetic energy is dissipated through heat and stuff, right? So you crash your car into somebody, you're gonna feel a lot of fire. That's radiation. That's energy leaving the system.
And then that's eventually going to redound to accelerations of the charged parts, which then in turn produce light. And when an object has a different amount of heat, it produces a different amount of light. We already know this. I forgot. It's like Wien's equation or something. Stefan something. I forgot. Yeah, there's some equation that just explains, how much light an object emits as, black body radiation based on its temperature. So if the temperature goes up, it actually, if it collides, the temperature goes up. If the temperature goes up, it emits more light. So, okay, I'm getting it.
Okay, yeah. Yeah, obviously there's a lot more context.
Its mass must have been greater in consequence of it having been in motion. Indeed, if its kinetic energy when it was in motion was k, then during the process of coming to a halt, the body must have lost an amount of mass equal to k over c squared. If its mass after coming to a rest is m0, then this in turn implies that its mass while in motion, m, was equal to m0 plus k over c squared. This is relativistic mass. It's not some ill-defined abstraction. It's the literal mass that a body acquires in consequence of its motion. That is, if we have some body at rest and we want to accelerate it via some external force, then what the theory of electromagnetism tells us is that the only method we have available to us is to essentially pelt the body with light or photons. But since these
So that was part of the video that a lot of viewers brought up objections to, and if you try to extend this context of this video to microscopic situations, like intercharge interactions, it's definitely much harder to see how that would apply. But yeah, the essential premise of this model is that for large-scale mechanical accelerations, every time you push on something, every time you accelerate something, you are essentially just shooting it with photons, trillions and billions, quadrillions of photons to get it to move.
Yeah. So for example, when I push on a box, the electron shells in the surface of my hand are basically, crudely speaking, like shooting photons at the electron shells of the surface of the box.
Yes. So again, we can pretend that these photons are little bodies of mass, right? So when you just imagine putting your hand up against a box and pushing it, you're just shooting all these tiny little particles at the box to get it to move.
Yeah.
And,
or to say it a different way, there's an electromagnetic interaction between the surface of the hand and the surface of the box.
Right. Is this fundamentally what's going on at the very, very microscopic level? Probably not, no. But it's a basic model that
sums over whatever's going on there.
This
provides us information about that summary,
right?
That true large scale phenomenon
is a equivalent way of looking at it, in certain contexts. So.
Photons are electromagnetic waves, then like all other types of waves, they carry mass. Thus, by absorbing some amounts of these photons, the body is also absorbing a very real inertia, one mediated by the precise quantity of kinetic energy k the body requires for its motion.
Here's where we have to discuss another big thing, which is this is where the model really implies that everything kind of has to be waves, because if the body absorbs the inertia of a wave, the wave only has that inertia in virtue of being in motion. So this basically implies the light didn't vanish or just mysteriously get absorbed. It's in there still moving around. Does that make sense?
Kinda, but I mean, isn't so the matter wave is now propagating through the ether faster as a result of gaining the waviness of the light?
I think maybe it's easier to approach it from the photon in a box theory. All mass can be said to be physically indistinguishable from a bunch of photons in a box.
Yeah.
And so somehow the mass defines itself by trapping this light within its region, but the light still has to be moving within that region in order for it to actually carry that inertia physically.
I mean, yeah, and I mean it's not hard to imagine that. I mean, the light is just one manner of the ether waving. The matter is a different manner of the ether waving, and when the photon, when the light oscillation enters the matter oscillation, they just somehow combine into some joint oscillation inside.
Yeah, clearly there's a lot more.
And when
there's a
we're
lot
not
more
clear
going
on the details of
Yeah.
that. Yeah, we're not clear on the details of that yet, but we still are producing a self-consistent picture
Yes.
of how this might actually work. And we're starting to crudely form the high-level facts.
Exactly. Yeah. So, all right.
Now, the kinetic energy K here is not the 1/2 mv squared expression that you might be thinking of, because that expression only holds under the assumption that the mass of your body or system isn't changing with speed. But here again, the fact that our body can only undergo motion by absorbing or emitting mass means we are working with a variable mass system. And thus 1/2 mv squared no longer applies. Instead, we have to use the strict definition of K, which in infinitesimal form is dk equals f dx, or equivalently, dk equals v dp. If we also want to expand the infinitesimal of momentum dp, then this requires the chain rule. That is, dp equals dmv equals mdv plus vdm. This means the correct expression for kinetic energy in any classical system which features a mass flux is, in infinitesimal form, dk equals mv dv plus v squared dm.
Okay. So this is a huge point. We didn't really realize until like the actual production of this video that we took a good long look at this equation and said, wait, E equals mc squared pops out of this equation.
Oh.
And this is the first time we realized, well, is it not just wave mechanics? So if this is the expression for kinetic energy as defined by Newton's laws.
Changing
right?
kinetic energy, yeah.
Changing kinetic energy. So if the mass of your system isn't changing, this term goes away, and kinetic energy equals 1/2 mv squared, right?
Mm-hmm.
But on the flip side, if the velocity of your system isn't changing, but the mass of your system is changing, then energy becomes v squared times m, with v being the velocity of the system. So that integrates to E equals mv squared, or c squared if we want to use that.
Well, but why do we get to equivocate between V and C? You keep doing this.
Well, I'm saying V is not changing. So if you assume that V doesn't change, right?
Oh,
then
and the only context in which V wouldn't change would be when it's already going the speed of light?
Well, I'm using C here in a general, C to stand in for a velocity that isn't changing, right? Because when we use V, we think about a variable velocity. So it doesn't have to be C the speed of light. It can be, maybe we should call it W or something, right? It's a speed that's constant.
Mm-hmm.
But this equation tells you, Newton's very basic definition of kinetic energy tells you, I guess Newton didn't kinetic energy, but from Newton's laws, that the energy of a system whose mass is changing, but its velocity is not changing, is going to have an energy that's equal to E equals mc squared.
That doesn't sound right, dude, because why do we get to just pretend V and C are the same here?
No, I'm not saying that. I'm saying it's going to have an energy, a system whose mass isn't changing,
mm-hmm.
who's traveling at a certain velocity. Let's call that velocity W, right?
Mm-hmm.
The energy of that system is going to be mw squared. Like,
but
well, I
what
guess
does
that's
that
not true
have to
because
do
this
with
is the
MC
change.
squared?
This is the change in kinetic energy, so it's not technically going to be the mass is changing. What I'm trying to say is that mc squared is baked into this second term.
But I don't see how when it's W squared and not C squared.
Well, okay, I think I've confused you too much. We'll come back to this topic.
All right.
All right.
But from Einstein's proof of mass-energy correspondence, we also know there's a second classical expression for dk. That is, dk equals c squared dm. Equating these two expressions, we can rearrange and collect terms to arrive at the following relation. 1 over m dm equals v over c squared minus v squared dv. Next, integrating both sides and putting in the appropriate bounds, we can solve for m in terms of v. And, well, can you guess what happens? Yes, we arrive almost miraculously at the expression for relativistic mass, and all without invoking a single postulate of relativity. Now, from this expression, the other...
Hang on. You used a certain assumption, and I just realized that I don't understand the justification for it. dk equals c squared m. Where did that come from? Yeah, where did that come from?
So specifically, if you want to ask where it comes from this earlier equation that we already derived.
Oh, okay. Let's see it.
Blah, 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 blah. Yeah, there we go. Gotta watch the ads.
If its mass after coming to a rest is m naught, then this in turn implies that its mass while in motion, m, was equal to m naught plus k over c squared.
So if you can just differentiate this equation with respect to, m and k. So
Okay, so dm
m naught's a constant, so that goes away.
So we could just bring c squared over to the left, then differentiate
Right.
both sides, and then it's c squared dm dk.
Right.
C squared dm equals dk. Boom. Yes.
Right. So that's where it comes from classically. Yeah, some people objected to that too. I think they thought it was like a snuck-in assumption or something. It's not sneaky. We just didn't.
It's just hard to see how
make
it
it-
was established earlier.
It could have used better.
Okay, and let me make sure I agree with this equation now. Was this established earlier?
So this comes from. This comes
Yeah, I mean
from.
this. I mean, the way I would think about it is that it comes from the Einstein derivation with the box, where we presume that light carries mass, basically. And so if light carries mass, and if light is the fundamental cause of macroscopic bodies gaining speed, then when the bodies get acted on by light to gain speed, they're also gaining the mass of that light, and that leads to this here equation.
Yeah.
Cool. I'm on board.
All right. So brings us to.
At the expression for relativistic mass,
Gotta
and
watch
all
this
without
again.
invoking a single postulate of relativity. Now, from this expression, the other supposedly relativistic expressions also follow: kinetic energy, total energy, and the relativistic dispersion equation.
So yeah, it's important to know that once you have this expression, you can derive the dispersion equation. A lot of people like to object and be like, dispersion equation is the fundamental one. No, it's not. It's again where they assume they try to argue by starting out by assuming relativity to be true, and then so yes, I don't know how many people were there, but once you have relativistic mass, kinetic energy you can get from the equations we already had, just integrating it differently.
Yeah, see,
And then you can combine that to get total energy, and then you can rearrange that all to get E equals PC. You have to throw in the E. You have to throw in the classical wave equation E equals P times C, and you can substitute that in, and then that gives you the dispersion equation.
yeah. See, this is great, because this is a superior way of deriving it. Instead of deriving it from just, assuming the space-time geometry of relativity, or better yet, really what you're, unbeknownst to you, what you're really doing is you're deriving it all from just a convention. You're treating a convention as though it's a law of the universe. That's not a valid account of the causes. this is a possibly valid account of the causes involved.
Yes.
It might even be provable, by the way. Like I'd have to formulate this myself to see if but I suspect you could prove this. You could just you could say, yeah, this just follows deductively from a bunch of basic stuff we already know.
I feel like that would be a pretty simple case. I mean, again, there's the issues of reconceptualizations. Are we reconceptualizing mass or not? But definitely.
But I think that's valid. I think there's an argument for that. If you don't want to capture that fact by conceptualizing mass, fine. Like, capture that fact by doing something else, but you'd still get equations that led from that principle to all of this stuff we see on the screen. I think it seems like you'd be able to.
Yeah,
it seems like, to me, it seems like that thought experiment with the box and where you enforce the center of mass, that accounts for a certain fact, which then leads to the rest of this, basically. And no matter how you want to conceptualize in order to capture those facts, you're going to end up with these equations. And so you're going to end up with an understanding of something involving the way light gives motion to matter, and then matter has different properties as a result of that action.
Yes. Sounds fair. We're almost to the end here.
Meaning the whole arsenal of relativity has just dropped into our laps, classically. Here indeed we observe only the consequence of the classical fact that electromagnetic waves carry mass or inertia, and, in being responsible for any externally applied force, consequently must deposit their inertia into ponderable bodies.
Mm-hmm.
Thus, when we ask the question, what causes relativistic mass, we can now give the answer that modern physicists can't. Relativistic mass is caused by the absorption.
Some people complained about using AI overviews to give general consensus. I think that's pretty fair. Like, AI mostly just scans what the general information that's already out there is and regurgitates it for you.
Yeah, I mean, anyone who goes against that consensus, like, good for them. But like that is the consensus. I've heard that.
Yeah, and if you really don't trust the AI for some reason, like, you can sort of comb through like Stack Exchanges and stuff and other areas and textbooks and stuff, and that is the consensus. Like, that's pretty much what the consensus is today. And I think AI can be trusted to do one thing. It's to spit out the most common viewpoint. So it's
of wave inertia by a body in order for that body to undergo motion. This not only reveals the physical mechanism we have been seeking, but it also grants us a deeper insight as to why matter cannot travel faster than light. That is, consider a body with inertial mass m moving at essentially near light speed. We can write its momentum as approximately mc. To accelerate this body further via some external force, the only option we have is to pelt additional photons at it along the direction of its motion. Let's designate these photons as having mass little m, speed c, and momentum mc. After these photons collide with the body has a new mass, m plus m, and some new velocity, v. Now, by conservation of momentum, the initial momentum, mc plus mc, must equal the final momentum, m plus m times v. Factoring out the c on the left and canceling, we see that the new velocity of the system remains c. A result which holds no matter how great the mass of the photons we throw at the body is. This picture, meanwhile, also accords with energy conservation, because with the velocity of the system no longer changing, the change in kinetic energy winds up being entirely dictated by the change in mass.
Yeah,
so that was the point I was trying to make earlier, yeah.
So, I mean, it only applies to a situation where the body is already going the speed of light and therefore can't accelerate more. But it can still gain the energy of the light deposited in it.
Yeah.
The analogous image I put in my head here is I imagine a train moving at a certain speed. Then I imagine an airplane flying above the train at exactly the same speed. Then the airplane drops a package onto one of the cars of the train. So the package is going as it falls, the package is going the same speed as the train. And so the package just simply, lands on the train and just sits there, or is now, and it was always moving along with the train. So the train gained mass, but it didn't gain speed because duh.
That's a really good analogy. I like that a lot.
Cool. Yeah. Thanks.
Yeah. No, that actually makes a lot of sense. Yeah, you're right.
It's like that. It's as simple as that. Only there's a little bit here because you're treating the limiting case where the mass is going almost C. But if you treat the limiting case where it's like really, really close to C, then the light truly cannot add anything to it.
Right.
Yeah.
So you're the airplane above, and you're just dropping more light packages that don't affect the motion. So
right. Although this light was able to catch up to the mass because the mass is going a little less than C, so the light does catch up, but it doesn't make
infinitesimally close to
it's an infinitesimal.
C.
Yeah, it makes very in the limit where the body's going C or is approaching C, then this adds only this much kinetic energy.
Yeah.
Yeah.
All right.
Thus, though true that it requires infinite energy or mass to reach the speed of light, the reason behind this is quite simply that the conservation of momentum, in conjunction with the conservation of energy, sensibly indicates to us that no body or entity can be accelerated beyond the speed of the entities which are being used to accelerate it. Now, of course, there's still a lot more about
Okay, so the last point here. So some viewers brought up some interesting points here, and said that if they made an analogy to sailboating. So if you sailboat downwind, you can never go faster than the speed of the wind.
Mm-hmm.
Like that's the maximum velocity you're gonna acquire. And this picture here is very analogous to that kind of thing. Like that's why you can't travel faster than the speed of light. The same reason you can't travel faster than the wind on downwind when you're sailing downwind. But then they were like, well, sailing upwind, you can travel faster than the speed of the wind.
Mm-hmm.
Basically utilizing the same principle that airplanes use to fly in the air. You have two sides of the sail, and air rushes across both sides of the sail, but it rushes across one side of the sail at a different speed than the other side of the sail. And the difference in speed creates a pressure gradient, which then pushes the sail and the boat in the direction of the gradient.
And that gradient is still there after you've reached the speed of the wind. In fact, the gradient probably gets larger once you've reached the speed of the wind.
Yes,
and then the drag forces of the hull and the water eventually, cancel, and then you reach some top speed. Yeah.
So some viewers are like, well, why couldn't you just do the same thing here and accelerate a body beyond the speed of light using some similar mechanism?
Mm-hmm, mm-hmm.
Which I thought was an interesting objection at first. However, I don't think if light doesn't really ever travel at any speed other than c, it means it would be going around either side of your sail at the same speed. Like it wouldn't change. The sail accelerates because the wind, the air is moving across it at different speeds on either side. But if you've got like a light sail in a vacuum, it's the speed of light would still be moving around at the same side.
Yeah,
I don't think that
light's
objection
not
would really...
fluid that lowers in its pressure when it starts going faster, and it doesn't go faster. Yeah, I mean that's your point.
Yeah.
You can't get the light to go faster around one side of a sail.
But it was kind of a neat idea.
Yeah, I mean, I think the way I would think about that question is just that, oh, that's interesting. I'll keep that in my back pocket in case there's some, something else to follow up on there. But yeah, for now, it doesn't seem to really make sense.
All right, so I've got one last big point I need to make here. then we can finish this video. All right, and this is a big thing that was left out because it just didn't fit, but it's sort of important, so I want to address it. So let's go to somewhere where the light is being accelerated. Okay. Back to the model of what's causing the motion, right? The light, you're firing a light. So as charged bodies, when they accelerate, they radiate, right? Mm-hmm. And it turns out neutral bodies, all bodies do this. Every body radiates as it accelerates. So the model here tells you, to accelerate a body, you have to shoot radiation into it. It has to absorb radiation. That kind of doesn't seem to make sense, though. The body's also emitting radiation, right, as it's accelerating. Yeah. It sounds confusing, right? Mm-hmm. So it turns out, it's really interesting. So it turns out the body that's accelerating is both absorbing light and emitting light at the same time. And if we go back to the derivation scene here, in the production we depicted it. Okay, that line was kind of botched because an accelerating rocket doesn't have any incoming mass, right? It's just ejecting mass. That was not very precise. But so the analogy breaks a little because a body of mass would be like a rocket that's both ejecting fuel and taking in fuel. Mm-hmm. But it turns out the rate of flux of incoming to outgoing fuel isn't the same, and it varies at a very interesting rate. So when a body is at rest and you start pumping radiation to it to accelerate it, it's going to essentially eject almost all that radiation back out. So there's it moves because you've pumped radiation to it, and then it shoots that radiation out and moves even further. As the closer you get to the velocity of light, the frequency at which it ejects radiation decreases. So it ends up
the rate of ejection, you mean?
Rate of ejection, yeah.
Yeah.
So it begins to take on more mass than it's ejecting. So that's why for very low velocities, the mass is pretty static because everything you pump into it essentially gets ejected out.
And the mass at any one moment represents like an equilibrium condition, basically.
Yeah.
Like in a chemical equilibrium where like the rate in and the rate out determines some kind of settling, some sort of like quantity that it settles on for both reactants and products. Yeah.
What really interesting thing we came across, doing this video, they said you don't technically need wave mechanics to derive this. So if you look at this on the screen here, if you assume you have a universe where you have masses and you can only accelerate those masses via tiny balls of that move at a specific one speed only, right? So you've got your general masses that can move at any speed, and then you've got these tiny balls, photons we'll call them, that have a specific mass and only move at one speed, c. Mm-hmm. And if you want to accelerate your mass, you can only do so by pelting it with these tiny balls. So just by conservation of momentum, if you calculate, you can calculate the mass of the system based on its velocity, right? Because to get the mass to move at a higher velocity, you have to pelt it with more balls. And it ends up becoming, a bunch of tiny balls stuck to the big ball. Trying to remember professional here. So, what the equation you get, the expression you get, is that the mass of the system is velocity dependent, just like relativistic mass, but it's not the rest mass times gamma. It's rest mass times 1 minus v over c, which is a Doppler shift.
Oh.
Yeah, it's a Doppler. Then when it's very interesting. It's a Doppler shift. So
term, yeah.
When you first came across it, it seemed like, well, is this wave behavior? What's going on here? But the problem with that is that picture doesn't conserve energy. So if you're assuming these inelastic collisions, energy is not conserved. And while you get some features of relativistic mass, you get that mass increases with speed. You get a speed limit that's the speed of light. You don't conserve energy. So the picture of just shooting something with tiny balls and assuming the balls stick isn't correct. So then we're throwing around some more ideas, and well, we thought, what's the expression if a body mass starts out with rest mass m and then accelerates by just ejecting tiny balls of mass at speed c? And if you calculate that, you get that the mass of the relativistic mass equals the rest mass times 1 plus c over v, or v over c, which is the Doppler shift in the other direction. Do you follow?
Yep.
So once you have that, you can put together that, well, the gamma factor is just the geometric mean of these two Doppler shifts. So basically, it implies that you can model this with just tiny billiard balls that move at speed c if you assume that the billiard balls are being accepted into the system at a frequency of the 1 over 1 minus v over c, and being ejected from the system at a frequency of 1 over 1 plus v over c.
And does that picture as a whole conserve energy?
That conserves energy and gets you the correct expression for relativistic mass.
Huh.
Which is really interesting.
Yeah.
So something's going on here.
Yeah.
I think it's all wave nature related, but
you can zoom out and still understand the basics with this crude particle picture.
Yes. So if you shoot a particle like in this picture, dm plus m, the particle, this can't be the new, if the mass of the particle is dm and the mass of the original body is m, this new mass is not correct because it doesn't conserve energy. Some of that mass has to be shot back out.
Mm-hmm.
And that's what happens, in the light picture as well. You shoot a bunch of photons at a low velocity, a lot of those photons get shot right back out. And they're shot out to balance, essentially keep the checkbook of energy at the correct level. So I don't know what that means at all, but it seems like it's something.
Yeah. Yeah, that is very interesting.
Very, very, all right, out there. All right, we're going to finish the video now.
Has to unpack here, including what the nature of wave inertia ultimately implies. But with this final totem of relativity now classically accounted for, we're at last in a position to deduce the principle of relativity, that is, the empirically observed two-way invariance of light, purely from classical principles alone. Meaning everything modern relativity is required to postulate, we will soon be able to derive. As always, this has been Dialect. Stay tuned.
Yeah, that's really cool. This is really coming together. It's really all, there's this overarching project that Dialect has been doing, and now it's starting to see. Now it's definitely coming together here.
It's still hazy, but it feels like the pieces are finally starting to fall into place. And
well, it was hazy at first. Now it doesn't seem hazy. I'm seeing, okay, the big picture is
well, hopefully your understanding is improved a little. And yeah, it's hard. It's difficult to fit so many tough concepts into 20 minutes.
Yeah, but it's working out.
I think we're
working. Yeah, the structure's coming together because and it's important because in modern physics we've presumed that we need to account for these facts using radical changes in our metaphysics, but what your organization has shown here is that is not necessary.
Yeah, that's definitely what we hope to achieve and keep achieving in future videos. And so I just wanted to address finally the mass question, because there's a central question here. What is mass? Obviously, it's a question we don't really fully know. I know you brought up the point that you feel like we're reconceptualizing mass, but again, I can't say personally speaking that I'm like 100% familiar with Newton's Principia, but I don't feel like anywhere he states that mass is a specific quantity of substance. I could be wrong on that. Maybe something worth looking into.
That's my personal way of framing it.
My understanding was that it's always been P over V, and that we associate it with the idea of a quantity of some existing substance, but that it's really just giving weight to motion. It's giving weight to entities in motion, like how much can this entity push or pull other entities.
But if you define mass in terms of momentum, then there's a question of like, well, what is momentum then? Because you can't say you now can't say momentum is m times v, because now it's just a circle. So
that's a bit of a different issue. Yeah, there's always going to be a level of circularity in definitions, right? So
I don't think so,
because we have only a finite number of definitions. And,
but eventually
so
your
they're gonna refer to
definitions
each other.
might point. Some of your definitions might point to other words, and then you have to look at their definitions. But the right way to, but you shouldn't get a circle. At the end, you should get simply ostensive pointing towards reality. So, for example, like if like it might point to something like, well, it's the quantity of material. And what is quantity of material? Like, okay, well, it's based on the presumption that like in some like uniform material, if you double its volume, then you double the quantity of material. That's something you can just directly perceive. So in my view, that's how you justify
but you're still not going to
escape.
You're not going to escape circularity, because you're still going to, if you try to define material further, you're going to end up, with circularities there.
Material is just, you see it, like, here it is. Here's the material. Like,
how do you see it? How do you see it, brother?
What's that?
How do you see it? How do you see it? Right,
well,
you have to measure
a different
it. You have to find a way
involving
to measure it.
light acting on the eye and stuff. But
so,
if you think that the senses really do give you evidence of what's going on in physical existence, and I think they do, and we can get into that philosophical discussion, but I think they do, it's enough to just simply say, I'm aware of this substance, and that's it. I'm just allowed to say substance, and I mean this right here, and other things like it.
Well, I think, if we don't want to rely on our senses, we want to rely on objective measurements, right? Then we've got to refer to these conceptual explications: mass, velocity, momentum, energy, that kind of stuff. And yeah, so mass, momentum, and mass, like what's the difference? Well, the difference is quite simply that you can associate, you can make momentum a function of velocity if you want. You can also make mass a function of velocity, depending on how you choose to express it. So no, there's some level of circularity, and yeah, do we know which one's more fundamental? Maybe one's more fundamental, maybe one's not. At this level, I personally don't see. I feel the concept of mass to be highly instructive and highly helpful in understanding and conceptualizing what's going on. The whole relativistic argument is that mass is now useless. So let's just talk about momentum. But like in the rocket picture, like the rocket picture, it's got a variable mass, and you could just talk about momentum, but I think you really lose something fundamental that's going on there if you do that. And you lose the picture of where the substance in the rockets, what's happening to it, where's it going, where's it coming from. So I mean, your objection is fair.
Yeah, I mean,
it's a difficult question.
In that last statement, you referred to substance, like your justification referred to like the actual substance going in and out,
right?
Or out, just out in the case of the rocket.
So yeah, in a sense, I'm agreeing with you that mass is an idealization of substance. But at the same time,
for me, like what's funny is I agree with what I'd have to think about it more to be certain, but based just so far, I agree with what I see in this video, but it all hinges on me redefining mass based on a desire to capture the fact that if you have a set of interacting bodies and light, and light waves, then there's a uniformity to the interactions. And one way of capturing that uniformity is to redefine mass and to say that the center of mass doesn't change.
I mean, maybe you're right. Maybe I'm treating mass as a substance, and that's why relativistic mass was so important to explicate, because I want to treat light as a substance. That's the thing, is I don't feel like it goes both ways. Like, yeah, the inertia of a wave is kind of rejecting the conceptual substance notion of mass, right? Because you're signing an equivalent mass, and you're just saying inertia is real, but the mass isn't, right?
You don't have to, yeah.
So, in one level, you can say that a wave is equivalent mass, so the mass isn't really there, but it conveys a very real inertia. However, on another level, the wave only conveys inertia. It only carries momentum because its constituent parts have mass in the classical systems, right? So the mass of the wave isn't the actual mass density of the wave, like the substance that's there in the wave. It's how the substance is moving, but that substance carries momentum because the constituent medium parts that are moving have mass. Is assumed in the classical picture to already have mass, which I guess would agree with your view.
Tell me if
like
this resolves your confusion. I look at this top down. I start by thinking about the ether. And I say, okay, the ether has these parts, and the parts vary in some property. Now, by the way, the parts aren't bodies. They don't have mass. They're just existence. Okay? I'm not saying they have mass, and I'll tell you why in a moment. I'll tell you why I don't give them mass in a moment. So these entities exist, and they have properties, and they can pass their properties around to one another. Now, notice I didn't say that they move like your little weights in your animation. Yeah. I'm saying they have a property, and they can pass that property around. Now, maybe the property is like a literal physical movement, a spatial movement, but maybe it's some other property. All I know is that it's a property. Now, as this wave of property, like the movement of this property through the medium, as this wave of the property starts moving through the medium, there are rules about how much, there's things we can say about it. There's how much of waviness is there. There's how difficult is it to change the speed of this wave. And this is mass. Mass is emergent from whatever the medium is doing at the fundamental level. And it's important to differentiate mass that we observe in the macroscopic movement of things versus whatever the medium is doing to produce those properties and that inertia, that resistance of the whole wave to accelerating. And when you do that, you don't give the little bits of the ether mass, because mass is something that emerges as a property of waves of the ether.
Yes, yeah. Well, first of all, you're going like 3 layers deeper than me, for sure.
But I think we need to do that. Otherwise, we get tied in circles.
So you're trying to like say, let's adopt a new kind of conceptualization of what's going on a metaphysical level. Whereas I'm kind of trying to avoid that, but I would object to that because, if this wave model comes from just basically taking classical Newtonian physics and you're seeing how it works for waves, and all these waves waves in classical systems, waves like sound waves, waves on a string only carry momentum because their individual parts already have mass. So the mass is in that sense an intrinsic part. So this would seem to imply that if you wanted to go after an ether model, that the ether itself already has an intrinsic sense of mass and a resistance to how much it wants to be displaced.
And the parts are moving. That's one way to think of it, but you don't have to think of it that way. You can just say there's some additional property, and what we call mass and inertia emerge from that different property that the ether has and it's passing around.
I mean, that could be, could be something. I guess, yeah. Well, definitely, there are lots of ways one could keep taking this. So
yeah, but either way, this is a step forward. This really gets me thinking, and I think one additional step that we might take in the future is to consider this wave, these aspects of wave mechanics and integrate it with the other aspects of how the physical phenomena we've experienced require a wave mechanics. Like, how does this integrate with the aspects of quantum mechanics? How does this integrate with the nature
this is definitely
of gravitation?
Definitely headed towards quantum mechanics.
Yeah.
We feel, at least it seems like it's gonna link real quick.
Yeah.
So is there anything else you'd like to talk about before we close out here?
No, that's I think we've given some good supplements to this to help people see where this is all going and to see the deeper meaning of it all.
Well, I want to extend the gratitude on behalf of the Dialectical channel for taking the time and effort to sit down and talk to me today. And hopefully we helped elucidate a few things for channel viewers and all that stuff. And hopefully they won't be more confused than when they started. But yeah, man, it was a pleasure having you on. You always bring up great insight and great thoughts and great commentary. And you've got a very keen mind. So appreciate it that you brought it here for us today.
Thank you very much.
And all right. Well, until next time.
Till next time.